Hi everyone! In this video, we'll break down the rigging process of Thor's Hammer in 3ds Max, adding squash and stretch effects. A subscriber asked me about this a while ago, pointing to an impressive Thor's Hammer rig by the Agora Community done in Maya. When I finally had some free time, I decided to take on the challenge and recreate a similar rig in 3ds Max, adding my own tweaks and preferences. We'll start with the basics, rigging the handle. Here, we'll set up the base twist and add a squash and stretch system so the handle dynamically stretches during swings. Next, we'll move on to the hammerhead, making it more dynamic. We'll add extra controllers to achieve expressive twisting, squashing, and stretching. Then we'll handle the strap. It's quite straightforward. We'll build a simple bone chain, link them to controllers, and parent the whole system to the global controller. Finally, we'll rig the speed trail mesh, setting it up to simulate a dynamic wind flow or motion trail. This rigged model is already available on my Patreon. You can download it there and support my work. Before we dive in, let's look at the model and its topology. Modeling and texturing took a day, but the rig required much more effort. Through trial and error, I developed an optimal hierarchy. All I ask in return is your support. Please like and comment on this video. It's my best motivation to create more breakdowns. Let's take inspiration from the Agora Community example. They made a great rig in Maya, and we'll try to replicate its logic in 3ds Max while keeping all the functional features. Alright, now that we have the plan, let's get started. To keep this lesson concise, I've pre-organized the layers. We'll begin by placing helpers. Create points at the base, center, and top of the handle. We'll use these to align our controllers, and then we can delete the points. I use points because it's the fastest and most accurate way to match the controls to the geometry. Now, select all 3 controllers and reset their transforms. This ensures all pivots have the same orientation. Let's change the shape of the center controller, since it will handle the curvature of the entire handle. I want it to stand out visually so its function is clear at a glance. Now create the COG, Center of Gravity, controller, and a global master controller to manage the entire hammer. Reset the COG's transforms. Since it was created in the left viewport, its orientation differs from the others, and we need to fix that. Then, link all handle controllers to the COG and the COG to the global controller. Double-click the master controller to select the hierarchy and freeze transforms. Alt-RMB, freeze transform. Let's look at the reference again and analyze the key features in slow motion. Notice how the central handle controller doesn't automatically stay between the head and the base. The original authors likely preferred to animate the bend and rotation manually for microcontrol. Replicating that is easy, but I want to go further. I want the central controller to automatically inherit the average position between the head and base for a more flexible workflow. During editing, I noticed a detail I missed. The original had extra controllers along the handle for more detailed bending. The reference video is so dynamic, I missed it at first. If this is critical for you, let me know in the comments, and I'll record a separate video on adding those. Let's make the central controller dynamic. Create a group for it and open it immediately. Align the group's pivot to the controller's orientation and freeze transforms to zero out the values. Now, let's set up the automatic position averaging. The simplest way is a position constraint, but it has downsides. For this rig, a float expression is better. Let's set it up. The formula is simple: start plus end divided by 2. This is the classic way to calculate the arithmetic mean and find the perfect center between 2 points. Assign our controllers to the start and end variables. It doesn't matter which is which, the result is the same. Just make sure to bind them to the correct coordinate axes. Repeat these steps for the other axes, Y and Z, so the controller is perfectly locked in the center in all directions. During testing, you'll see the central controller stays in the middle, but its orientation doesn't change. We need it to follow the handle's tilt as well. For this, we'll use a look-at constraint. Important, apply the look-at constraint to the group, not the controller itself. You'll notice the orientation flip. To fix it, go to Settings and change the Select Look-At axis from X to Z. Now, the central controller perfectly follows the top one while staying centered. It reacts the same way to the bottom one. This is exactly what we wanted. Create 3 points and place them exactly at the centers of our controllers, then parent them. These points will act as bones for skinning the spline that will drive the handle. Now create the spline. Turn on Snaps, Pivot Mode, and draw a 3-point spline by clicking the centers of the controllers. The vertices will align perfectly. As a perfectionist, I want the spline's pivot orientation to match the controller's. I'll reset the line's transforms, link it to the COG, and perform a freeze transform. If we move the center vertex, the bend looks too sharp. To fix this, change the vertex type to Bezier and adjust the handles. Now the curve is smooth and natural. Now for skinning, assign the points as bones and adjust the envelopes, influence radius. Using points to drive a spline is the most efficient method. Let's test it. As you can see, the spline follows the controllers perfectly, maintaining great plasticity. Regular viewers probably guessed, this is the foundation for a Flexi line. I have a detailed video on creating one, so I'll skip ahead to the final result and show how this version differs. Note, if you move the center controller and apply scale, transform to 0 only resets the position. You'll need to manually enter 100% for the Z-axis in the transform box to restore original proportions. How this Flexi line differs from my previous one. First, I used 7 points instead of 5 due to the model's complexity and topology. Second, the COG acts as the global controller for the system. I didn't want to clutter the scene with extra objects, since a separate main controller would just duplicate the COG's movements. Third, axes. In the Look-At settings for the drivers, I chose Z as the main axis and Y as the source axis for the up nodes. This is crucial for correct orientation. Fourth, I used a different float expression for the up nodes because there are 7 points. This expression is optimized for multi-level Flexi lines. Fifth, I placed the squash toggle on the central controller. It's the most accessible spot for quick adjustments during the animation process. Let's start rigging the hammerhead. We'll begin by creating the main controller, which will serve as the parent for all subsequent elements of this rig section. I'm planning to make the head rig dynamic. We'll set up a special switch that gives the animator huge flexibility and eliminates routine tasks. When enabled, the head won't just follow the handle, it will organically follow the curvature and orientation of the Flexi line drivers. When disabled, it will remain rigidly snapped to the top point. First, let's align the head controller's pivot to the top handle controller, both in position and orientation. To avoid cyclic dependency in the future, we'll parent it directly to the global controller instead of the handle. After that, make sure to freeze transformations. Now, let's create a group for the head controller and open it. Use Alt+A to align the group's pivot to the controller's position and orientation. Next, select both the group and the controller and freeze transformations to zero out all values. Time for constraints. Select the head controller group and apply a position constraint. Set the final Flexi line driver as the first target and the handle controller itself as the second. Repeat the process with an orientation constraint so the head inherits both position and rotation from both objects. Let's create the switch itself. Add an attribute holder modifier to the head controller. Press Alt+1 to open the parameter editor. Set the parameter type to Boolean and the UI type to check button. Name the parameter follow and hit add. Now let's link our switch to the constraint weights via wire parameters. Right-click the head controller, select the follow parameter, and drag the wire to the parent group. Time for the switching logic. For weight 0, keep the direct connection. For weight 1, type 1- at the beginning of the expression. This way, when one weight turns on, the other automatically zeroes out. Repeat the exact same step for the orientation constraint. Let's test our rig. With the follow button off, the head simply follows the main handle controller. Everything is working as expected. But once we activate the follow button, the head controller begins to bend, perfectly matching the Flexi line curvature. It looks very smooth. We now have a truly dynamic head rig in our arsenal. Now let's place the helpers. We'll create points and position them along the head model at key deformation points. Then we'll add controllers and align them exactly to these points. These controllers will be used for squeezing, stretching, and twisting the head. They will help us achieve that expressive deformation in the animation. Next, we'll create another controller and place it across, encompassing all 5 previous ones. It will be responsible for the overall squash and stretch of the head, as seen in the reference. We'll follow the same logic as in the original video. Select all created controllers and zero out their transformations. This ensures that all pivots have identical axis orientations, which is crucial for correct animation. Now, let's link the elements into a single system. Select the 5 inner controllers and parent them to the main cross frame. Then, link the frame itself to the main head controller. Double-click the master controller to select the entire hierarchy and freeze transformations to reset the coordinates. The hammerhead controller itself should only handle rotation. It doesn't need to be moved. So let's go to the Link Info tab and lock the movement on all 3 axes under the Locks section. We'll do the same for the 5 inner controllers. Lock their unnecessary movement axes. We need them to move strictly along the head, so we'll keep only one axis active and lock the others in Link Info. Create separate groups for the 2nd and 4th controllers. Open them, align the group's pivots to the controller's coordinates, and make sure to freeze transformations. Now, assign a float expression to the y-axis of our group with the familiar formula, start plus end divided by 2. The variables will be the two outer controllers. Why are we doing this? To ensure that the middle parts of the mesh distribute automatically when the head is stretched or squeezed. You won't have to manually set every point. The rig will maintain perfect proportions and smooth deformation on its own. Perform the same operation for the second group. Now, let's set up the twist. It's important not to overdo it. For a great look, remember that the handle passes through the head. Excessive deformation will look unnatural. Therefore, we'll limit the rotation by assigning a float limit controller to the corresponding axes. But before that, let's clean up the axes. To prevent the animator from accidentally over-twisting, we'll lock the unnecessary rotation axes in the Link Info tab. Keep only the axis responsible for twisting active. Now, let's assign a float expression controller to the y-axis of our group. We'll use the simple expression we already know, start plus end divided by 2. The variables will be the two outer controllers. This will provide automatic averaging of the central node's positions. After a lot of observation, I decided to take a risk and added twisting even for the central controller. In my opinion, it makes the rig look much more impressive. The key here is not to forget the limits so that the effect stays within reasonable bounds and doesn't break the geometry. Once we've set up the expression for the central group, we need to adjust the others. In the two groups where we already wrote the float expression, change the variables. They should now reference the central group instead of the controller itself. This will ensure the entire chain works correctly. Now everything looks truly harmonious. The controllers twist as a single organism. This will significantly simplify the animator's job, as the main deformation happens automatically. At the same time, if a unique bend is needed for a shot, you can always manually adjust the twist of each controller. Next, we'll add a series of auxiliary rectangular controllers, top and bottom for each main point, just like in the reference. They will handle the local raising and lowering of the top and bottom edges of the hammer, giving us even more control over the shape. Now, link the new auxiliary controllers to the main ones and make sure to freeze transformations. This creates a clean hierarchy where each microcontroller moves along with its parent. Let's set up the limits for the microcontrollers. For the working vertical axis, we'll assign a float limit to define a soft range of motion. We'll simply lock the movement on the other two axes in link info, as their only purpose is up and down movement. Create points and place them exactly under our new controllers, then perform the parenting. These points will later serve as bones for the mesh deformation. Having finished the main structure, we'll add the final row of controllers as in the reference. This time, we'll use points. Place them exactly at the corners of the hammerhead for the most detailed shape adjustment. Now, clone all the points. To quickly change their appearance, we'll use the Max Script Listener. With one command, we'll hide the box display and enable the cross. This is much faster and more convenient than editing each object manually when there are so many of them. Now, let's build the hierarchy. Parent each new point to the previous one, and that one in turn to its controller. After that, select the entire chain of objects and freeze transformations to reset the coordinates. As you might have noticed, I've placed controllers and point bones at all the corners of the hammerhead, parenting them to the main control objects. I've also set limits and constraints for them so that the corner deformation remains under full control.
Now let's move on to rigging the strap. Everything here will be fairly simple and fast. We'll start, of course, by creating points. We'll place them along the entire circumference of the strap. These helpers will serve as the skinning bones in the future. let's create a global strap controller and position it exactly under the bottom handle controller. This will be our main control node for the entire loop. I really liked the look of the controllers in the original reference. Let's create a similar shape for our strap. It will make the rig not only functional, but also visually clean. We'll parent our controller to the center of mass, COG. Then we'll create a group for it, open it, and align the group's pivot to the bottom Flexi line driver of the handle. To finish, select both the controller and its group and make sure to freeze transformations. Assign position and orientation constraints to the controller group targeting the bottom Flexi line driver. This part of the rig won't be dynamic. The model is designed so that the strap must always rigidly follow the base of the handle. However, we still maintain full manual control because only the group follows the Flexi line. The controller itself inside the group remains free, allowing the animator to manually add the necessary strap movements at any time. Now let's create auxiliary controllers for our bones and make sure to zero out their transformations. This guarantees that all elements will have a unified axis orientation, which is critical for predictable strap behavior. Next, link the point bones to their controllers, and the controllers themselves to the main strap control node. Finally, select the entire hierarchy and freeze transformations to reset the coordinates. And lastly, let's set the locks for the main strap controller. In the link info settings, lock the movement on all axes, as it should always stay in place relative to the handle, working only for rotation. And for the final touch, rigging the mesh for the speed effect. We'll add this smear trail as seen in the reference video, as it perfectly emphasizes the dynamics of the hammer's movement. Before we start rigging, let's take a look at the mesh itself. This is my first time creating such an effect. The trail had to be modeled entirely by hand. It might seem imperfect to some, but it's my first step in working with these types of elements. Well, let's get to it. But before we start, I should mention, rigging this mesh will also be relatively simple. We'll handle it quite quickly. We'll begin by creating a global controller for our trail. Just as we did with the hammerhead, we'll align its pivot to the position and orientation of the top handle controller. Next, we'll parent our controller to the global controller. We'll do this the same way we did with the head to completely eliminate any risk of cyclic dependency. Now, let's set up the dynamic rigging for the trail. Logically, it should be strictly parented to the head, but in the reference, we see the authors separating this mesh. Since there's a request for flexibility, let's make it dynamic. We'll follow the same steps as with the hammerhead. Create a group for the controller, open it, and assign position and orientation constraints. This will allow our trail to flexibly switch between follow modes.
There is a small difference here. We'll create another point at the top handle controller's position and parent it to the global controller. This point will become our second target. It will allow the trail to stay in world coordinates when the main weight is switched to it. Next, we'll create 3 controllers along the trail mesh. These will be responsible for the squash and stretch of the speed effect, allowing us to flexibly adjust its length depending on the impact force. Link all 3 controllers to the main trail controller and zero out their transformations. Then parent the point bones, each to its own control object. Finally, select the entire hierarchy and perform a final freeze transform to clean up the coordinates. During the testing phase, a small bug popped up. The trail controller isn't bending along with the head. I admit I made a mistake in the hierarchy. In the first constraint weight, I specified the top handle controller instead of the Flexi line driver, but no worries, we'll just reassign constraint targets and relink the parameters. It's a great chance to check our attentiveness. In the weight hierarchy, the first target should either be the driver or the bone. In our case, it doesn't matter as they behave identically. The main thing is that the trail inherits the bend. For the second weight, we'll use our world point to enable space switching. Now, let's reset the connection via wire parameters. For weight 0, set a direct dependency from our parameter, and for weight 1, use the familiar 1 minus formula at the beginning of the expression. Do the same for the orientation constraint. Now, during testing, we can see that everything works perfectly. Our troubleshooting paid off. The trail obediently follows the handles curved, and the switch correctly manages the weights. And now, skinning time, friends. I won't show the entire mesh skinning process. It's a long and tedious task, and I'm sure most of you already have experience with it. I won't be reinventing the wheel here. However, there are a couple of things that make this skinning process different from what you might be used to. Since we're using points as our bones, it's very convenient to use a filter when adding them to the skin modifier. Just type the bones prefix in the search bar to instantly find the right elements in the list. This is exactly why I recommend paying close attention to naming. It will save you a ton of time. The second point is the envelopes. By default, they are created huge for point helpers, so you need to scale them down immediately before starting the actual skinning. For many, this will be a new experience. Why didn't I use standard bones? Because they would require separate setups for stretching, which would add unnecessary elements to the scene and waste a lot of time. In this regard, points are much more concise and efficient. Well, friends, it's time to see the results. First, I'll scale the global controller. This is the best way to quickly check if the hierarchy and skinning are holding up. If the mesh scales uniformly without breaking, it means the weights are assigned correctly. Next, I'll move on to the COG controller and test its movement to ensure the main parenting is solid. Now let's take a look at the handle. As you can see, all the deformations, squash, stretch, and twist, are working correctly. The mesh follows the rig without any artifacts, and everything looks exactly as intended. Looking at the results, I'm really glad I chose to make the middle handle controller dependent. It always maintains an averaged position between the two main points. Also, the dynamic head rig gives us a choice to have it follow the curvature or toggle that link off with a single click. Even the strap automatically follows the handle's curve. There's no need for manual keyframing to bend the hammer. Everything happens interactively. This will save a massive amount of time and effort, and I'm sure any animator would be thrilled with a rig like this. Now, let's test the squash and stretch of the head itself. As you can see, all deformations work in perfect harmony, maintaining the mesh's volume and shape. Everything looks very aesthetic and smooth. Let's play around with the scale. See how our hammer instantly transforms? It becomes flexible and alive in the best traditions of the cartoon style. The entire rig holds up perfectly, allowing us to achieve extreme and expressive deformations in the spirit of classic animation. Now let's use the cross controller to simultaneously manage the squash and stretch of all 5 head sections, just like in the original reference. The result is identical. Everything works smoothly, allowing us to change the hammer's silhouette with just a single movement. And now let's play with the microcontrollers parented to the main points. As you can see, we've achieved the exact same result as the Agora Community team. This just goes to show that 3ds Max isn't as limited as many people think. With the right approach, you can build complex rigs of any difficulty, standing toe-to-toe with any other software package. Let's take a look at the strap. It's quite straightforward here. We didn't use any complex expressions as there was no real need for them. These controllers do exactly what they're supposed to do, providing the necessary flexibility and manual control over the shape. And the final piece for today is the speed trail rig. We've set up a dynamic system for it. If you toggle off the follow button, you can freely move and rotate the trail in world space. But once you enable follow again and reset the transforms to 0, the trail snaps right back to its position on the hammerhead. Dynamic rigging is a truly powerful tool, and I'm sure animators will appreciate this functionality. In closing, I'd like to express my huge respect to the Agora Community team. They've built a truly incredible rig. For me, this was a real challenge, and I feel I've successfully met it by recreating their setup in 3ds Max and adding my own custom improvements. I hope you found this breakdown helpful. I want to give a special shout out to the subscriber who shared the link to this rig and asked for a breakdown. I truly hope this video was helpful and answered all your questions. For me, this was also a great experience and a real professional challenge. It was awesome to deconstruct this logic and recreate it within 3ds Max. Your feedback is what motivates me to create these in-depth tutorials. Just a reminder, the finished model with the full setup is already waiting for you on my Patreon. Your support helps the channel grow. Huge thanks to everyone for sticking with me until the end. See you in the next one. Bye for now.